the legs pinned to the ground. Now, if you now take this leg uh, to be pinned to the ground, and you turn the pendulum in the right way so that it looks like a, so this is, let's say this is the double pendulum where this one is pinned, then you can swing this leg, and then when the leg goes forward, so will this leg move forward. It will become so this, let's say this is the hind leg, it will move in front, and then you basically let go of the rear leg, the rear pin joint, and you put a new pin joint here. Then you have basically switching of legs, and you can basically simulate a legged system. So the double pendulum is sort of important in that respect. So here is a double pendulum. I'm going to put a few things here so that we can derive the equations. So there's a mass inertia to each link. There's gravity. Uh, let's call this G1 and G2. Let's call this O, this point P, and this point Q. What else? Let's say that the angle made by the first link with the vertical is theta 1. The angle made by the second link with the first link is theta 2. So this is theta 2. We can assume that each of these joints are actuated by some torques. So let's call that tau 1, and then this is tau 2. And what else? So now finally thing we want, if you want to describe the kinematics, is frames, right? So this is going to follow the same frames we wrote for that manipulator, which we used for doing the inverse and forward kinematics. So let's draw x0, y0 like this. You typically put x0, y0 the way you want it. In this case, I want y0 to point in the direction against gravity, and so I put it. But you could put, for example, you could put y0 like this, and x0 down. This is what some people prefer. Okay. Okay, then what you need to do is, however, the local frames, you need to define as per a convention. So this is going to be x1, which is going to be along the first link, and y1 right angles to the first link. And then we have x2, sorry, y2 and x2. Okay, now what happens is this thing gets cluttered. So what I normally do is I actually draw another figure just to show some other things in the diagram. So let's call this x, y, sorry, y1, x1, y2, x2. So one of the trick which people do is they describe all the axes on one figure, and they describe all the mass, inertia, and all in another figure. In fact, you want to describe the axis and also the name of the coordinates theta 1, theta 2, and also the points GP on that figure, which is the second figure I just drew. That way it's much easier to do the kinematics. O, P, Q. And then if you want theta 1 and theta 2. Okay, so the question is, find the equations of motion, okay, which is the hardest part, then simulate, and then finally animate. Okay, so what we'll do is again use the Euler-Lagrange method to find the equations. The first step in the Euler-Lagrange is to describe the positions of the center of mass, because we'll be using those to find the Lagrangian. Okay, so in this case, we are interested in the position of G1. Okay, and I'm going to use the homogeneous transformation. So I can find a homogeneous transformation such that H1 times G1 in the local frame. So this is basically the position of G1 in the local frame. And this is something I forgot to put in the figure. I also need to give the distance of, this is C2. And my God, this is C1. So C1 is the distance from O and C2 is the distance from P. Okay, so G1 is basically going to be the local distance of point G1 in frame 1, which is this frame. So that's not hard. Let's try to find H10. So H10, if you remember, it's basically R10, O10, 0, and 1. Okay, so what's R10? So R10 is the angle made by X0 with X1. Okay, now, so I need to write cosine something minus sine some angle. It's the same angle basically here. So can anybody tell me what that angle is? What's the angle which goes in here? It's the same angle, but what is that angle? It's the angle between x0 and x1, right?
Is it 270 plus theta 1?
Right, so it's 270 plus theta 1. 270 plus theta 1, 270 plus theta 1, 270 plus theta 1. And the reason is because you always measure the angle from x0 to x1. This is theta 1, this is x1. So it has to be the counterclockwise angle. So this whole thing is 270. And then you add theta 1, so that makes it 270 plus theta 1. Then we need to find the position of O1, which is the origin of frame 1 with respect to frame 0, which is the world frame, and that's 0, right? So it's 0 and 0. Okay, and so we can write G10 as so cosine 270 plus theta 1 is actually sine of theta 1. If you don't remember this, if you go to MATLAB and you type cosine 270 plus theta 1 and simplify, so simplify in brackets cosine 270 plus theta 1, it'll actually give you the right value. That is sine theta 1. So this is what you get if you simplify R10. So this is the first part. The second part is O10, which is 0 and 0. And then we have 0, 0, 1. Okay, now G11 is basically the position of point G1 in frame 1, in this frame. So what's the coordinates of G1? Anybody? This one will be 1. What are the X and Y coordinates? What's the coordinates of this point in frame 1? Nobody? What's the X position of G1 with respect to frame 1?
C1.
Yeah, it's C1. And then the Y coordinate is simply 0 because the position of G1 is along the X1 axis. So that's G1. So if you if you want, you can write this as, this is going to be 3 points, xg1 0, yg0, and 1. And so then it's a matter of doing the multiplication there to find the coordinates of xg10, xg10, yg10. So this is the position of G1 in frame 0. Okay, now we'll do the same thing for G2. So G2 in frame 0 is H10, H21, G2 in frame 2. Okay, so we wrote down what is H10, H21 is going to be R21, O21, 1, and then we write G2 in frame 2. Okay, so let's let's write those down. So if you look at, okay, if you look at G2 in frame 2, the frame 2 is the frame which is going link 2. So it's going to be the local coordinate of 2 in frame 2, which is going to be C2 for the X, 0 for the Y, because the distance along the Y axis is 0, and then 1. So it's going to be C2, 0, and then we need to put a 1. S is a placeholder. Okay, now let's write the formula for this. So R21 is basically the angle made by frame 2 with respect to frame 1. Okay, so we basically have to do it something like this. So frame 1, if you remember, it was going along the first one, x1. Frame 2 was going this way. And so if you extend frame 2, it extends like this. So it's the angle between x1 and x2 in the counterclockwise direction. So it's theta 2. So it's simply theta 2. So all I need to do is write cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2, and then 0, 0, 1, and then I need to write the location of frame 2 with respect to 1. So this is P, and this is where frame 2 sits. This is O2, and I need to find the position of O2 with respect to frame 1. So I need to find its position in the coordinate frame of 1. So you can see that this point in this frame, x1 frame, is at a distance of L, because L is the length of the pendulum. I think I did not put it in that figure, but should have put it here. So this is basically L. And the other link is also of length L. Okay, so L, I forgot to put it, but it's basically going to be L, because that's the distance from for O2 measured along frame 1. So it's going to be L and 0, because the y coordinate is 0. And so we are now all set to do this math. So xg2 in frame 0, yg2 in frame 0, and then 1 equals whatever I wrote for h1 0, whatever I wrote for h2 1, which is this thing here, and then we'll have c2 0 1. Okay, so again, this is a math which you will make the MATLAB do. If you just specify these matrices, it will do the calculations for you symbolically. Okay, so this is computing the positions, right? And we are in the first step of the Euler-Lagrange method. The next step is to find the velocity of g1 in frame 0. And for that, we simply do, we take xg1 and then do the derivative, okay? I will show you how exactly it's done symbolically, but in principle, it's easy to do the derivative. So that's the x derivative. So, and then you will have to specify the y derivative. But once you have the expressions for xg1 and yg1, which we just got, it's very easy. So similarly, you can do vg2, xg2, yg2, and then you're done. So MATLAB will save it, and this will become, the second one is slightly lengthier than the first one. And it's a little bit of bookkeeping, but MATLAB does it for you. The second step is, once you specify the position and velocity, is to find the kinetic energy. And that's going to be 0.5, the mass of the first link, times the velocity. So now, there are many ways of finding the velocity squared. You can take the x component squared and y component squared. That's one way. The other way, which I by the way, is something which I did in the past problem on project as I actually did x dot squared plus y dot squared. The other way to do it is if you know the velocity, then you just write it. So normally velocity is a 2 by 1 vector, right? So what you do is to find the dot product, or x dot square plus y dot square, you take its transpose, which makes it into a 1 by 2, and then you multiply it with itself. So now you have 1 by 2 times 2 by 1. And then when you take the multiplication, it'll actually be a scalar. So this is going to be give you exactly the same thing we got for projectile, which is x dot square plus y dot square. So you can do the same thing for the second mass. Vg2 transpose Vg2. Okay, so that's the energy due to translation. Then we have the energy due to rotation. That's going to be half I omega 1 square, or theta 1 dot square, plus 0.5 I2. And now it's kind of interesting that the angular velocity in the formula for kinetic energy has to always be the absolute velocity. So in this case, we used absolute velocity for the linear part. For the rotational part, the absolute velocity for the second link. Okay, so if you remember, the first link as angle theta 1. The second link has a relative angle of theta 2. Okay, so the absolute angle made by the second link with respect to the vertical is going to be theta 1 plus theta 2. So I need to write here theta 1 plus theta 2, theta 1 dot plus theta 2 dot square. I cannot just write theta 2 dot square because that is the relative angle and we need the absolute angle. So that's the kinetic energy. The potential energy is mg times the height. This is going to be the position of first link, the y position with respect to the world frame, plus m2g, the position of the second link with respect to the world frame. And these now variables now are, they're actually part of this formula, which you'll get once you simplify that. So all that is taken care by MATLAB. Okay, so t and v are going to be some numeric some symbolic values which MATLAB takes care of, and you don't really bother manipulating them. MATLAB does all that. So the final step is for us to actually write the equation. So the Lagrangian is t minus v, and then we need to write the formula d dt dl dq dot minus dl dq equals q. Well, let's put j here, where qj equals, in this case now we don't have x and y, we simply don't have that notion, we just have the degrees of freedom, which is theta 1 and theta 2, and then qj is going to be tau 1 and tau 2, which corresponds to the two joints, or the torques to the two joints. Okay, so this is the bulk of the work which MATLAB will do for you using the same formula I wrote down in MATLAB. Okay, I'll show you that how it works. So once you do that, MATLAB will produce equations. Okay, so it will basically give you one equation, which will be EOM for Qj equals theta 1. So let's call that EOM 1. It'll also give you another equation, EOM 2, for Qj equals theta 2. Okay, and the last part is to actually put them in a form which you like. Now, in the past, we have found the formula for projectile as x double dot is something, y double dot equals something. Okay, so and that's fine for a projectile. Now, for a manipulator, we kind of know how the equations look like. They actually look something like this. There's a mass matrix times theta double dot. Again, I'll put down what theta double dot is, plus c theta theta dot times theta dot plus g theta equals tau. Okay, this mass matrix is actually a function of theta. So m theta is the mass matrix. It's only a function of angles. Okay, theta, where theta is theta 1 and theta 2 transpose. The c part is basically the Coriolis and the centripetal terms. acceleration terms. When you have non-linearities in the system, they typically come because of the Coriolis force terms, because there's a square involved in that. The next term, G, is only a function of the angles, not of the velocity. It's due to gravity. Okay, so if you do this, if you take the double pendulum and then you apply, it's not moving, it's stationary, or the accelerations are zero, then you need to supply a torque which balances the torque due to gravity, and that part shows up in g theta. So that's the torque you need to, or that's the acceleration of force you need to keep the double pendulum in static equilibrium. Okay, and so what you do is you basically, if you want to solve for theta double dot, it's basically m inverse. So I need to take these terms to the right. So we'll have torque minus C, and I'm going to drop the things in the bracket, minus G, right? This is what you get. So if you want to solve it explicitly in terms of x, theta 1 double dot, theta 2 double dot. So in principle, this is nice. This is good to do, but don't do this symbolically. That is, do not try to solve for theta double dot by taking a symbolic m inverse. And the reason is because when you look at that equation, that theta 1 will be a mess. It will be very long. So what people do is they actually store m, they store c, they store g. So they'll write the formula for m, they'll write a formula for tau, which is easy because there are two values, c, g, and then they will find m theta dot double dot equals tau minus c minus g numerically. So they'll put a numeric value to all of these things. And then in MATLAB, they'll numerically invert the inversion is done numerically. So what they mean is when they find this theta double dot, they will do m inverse tau minus c minus g. All the terms here will be numeric terms. There will not be a symbolic term here because the symbolic one is too much alphabets in it, and since MATLAB is a scripted language, it basically does all those computations, and there's a time associated with doing those computations. It takes a hell lot of time to do those computations if you take a symbolic inverse for m. So you always invert that numerically compared to doing the symbolic inverse. If you do it this way, you explicitly find the numeric values for this and then do the numeric inverse. It's much faster. So you do this every single time step when you want to do the integration. You just do the numeric computations of m, tau, c, and g, and then you do the numeric inverse. And I'll show you how it is done in the code. In the code, actually, there is a command called inverse m, which you could use, but MATLAB always recommend using the back slash to do the inverse. So the m slash is the same as m inverse. And MATLAB has a better way to solve for the inverse if you give it as m inverse instead of saying inverse m. Okay, MATLAB recommends this. Something to do with how MATLAB actually computes the inverse. Okay, so that's one piece about doing the inverse, right? Don't do this symbolically, and I'll show you how that works. The other thing which I wanted to talk about is how do you go from this piece where you have this equations of motion which has all these terms to the point where you are able to extract out the mass m, c, g, and torque. And this is a trick which I sort of learned by myself, and it's kind of helpful, which is once you have this EOM, so on the computer, you will have EOM1, EOM2. You will not know which part belongs to the mass matrix, which belongs to the C, because everything is a part of one expression. You also know that the form for M, the mass, the equations is this. So what we'll do is, in fact, it'll be something like this. So this will be EOM equals this. Okay, so this is what is hidden in EOM and you need to extract out. So what I do is I typically take this EOM and I do subs EOM and I put theta double dot, I put that equal to 0. So when I say theta double dot 0, it basically means theta 1 double dot is 0, theta 2 double dot is 0, and so on. So when I do this, if I put theta double dot equals 0, then the first part cancels off. And then what I'm left of is I'm able to get, I'm able to get the second term. So this gives me C theta theta dot plus G theta minus talk. Okay, so I can extract out this part from the first part by doing that. So whatever is left here is basically M times theta double dot. There's a way to extract out M matrix itself if you do, and I'll sort of tell you this, but I will not show you what Jacobian is right now. But if you do Jacobian of EOM with respect to theta double dot, then it actually gives you the mass matrix. Okay, so it basically removes the theta double dot from the expression, gives you the mass matrix, and I'll talk about the Jacobian next class or after that. So the Jacobian helps you to sort out M when you have a linear expression like this. If you take the Jacobian of this term, this whole term, with respect to theta double dot, it actually gives out M, and that's what is used to find M. So once you get M, once you get this, if you want to find, forgot to put theta double dot here. Okay, now once you got this expression, you have these terms, you still need to figure out this term from this term and this term. So this part is very easy because the torque term is simply T1, T2. So you kind of know this. If you want to sort these two out, then what you do is you further go and you say, so let's call this expression as, let's say B. Okay, when you take this B and you put theta dot as 0, so it will be theta dot 1, 0, theta 2 dot 0. And what happened is, because this, the way this theta dot is written, it's C times theta dot, the C part will go off, or it will jump out of the equation, and we'll be left with only G theta. And then whatever is left is going to be C theta. So if you do this, subs B theta dot 0 minus G, which you already found, then you should recover C. Okay, so this will be clear when I show you the equations and how they're derived. Okay, so this might be a little bit confusing, but trust me, once you look at the code, I hope this will be obvious as to how these terms come off from the expression. Okay, let me just run this so you see what the output is, and then we can work our way through the output. So what it does is basically gives you the equation. So it basically here gave me the mass matrix, which is, in this case, the mass matrix is a 2 by 2 matrix. So it gives you the different elements of it. The C matrix is actually a vector. The G is a vector, and then package. So what you need to do is, once you get this solution or this result, you need to copy paste in this part. Okay, so once you get this, what you need to do is you need to take this part, right click it, copy it, and then put it inside the other equation. So there is the right hand side, just like the right hand side for the projectile. You need to just copy paste them over here, and then the simulation will take care of it. Okay, now let's see how this part is written. Okay, so first you define symbolic variables like previously. The R, H, R1 to H12 was the same thing I wrote down in my formulas. So I get xg1, xyg1, xg2, yg2. This simply comes from the matrix calculation, which I just showed you. This is another way of deriving xg, yg. You can just do trigonometry, but it's going to work well for simple cases. Once you go to more complicated cases, you'll see that it's better to work with homogeneous matrices. So I just kept that just in case you want to verify. Then to find the velocity, Okay, so I could have done differentiation. I actually chose to use the Jacobian. Again, I will make what Jacobian is a little bit clear in the next class when I talk about Jacobians. Okay, I'll explain how Jacobians I use to find velocity, but you can find the velocity using Jacobians. It's a much effective way of writing the velocity using that instead of using diff, right? One way of doing that, finding the velocity, is to take this xg1, which is a function of theta1, and then doing diff of xg1 with respect to time. Another way of doing it is through Jacobian, and that I'll show you next class. So I got the velocity. I wrote the expression for the kinetic energy. Okay, same thing which I wrote down the formula for the potential energy, T minus V. And this step now is going to be a sort of a copy paste of what I wrote for the projectile. This goes from 1 to 2, where I define my Q's, Q dot, and Q double dot. Okay. Now, this is the part which I was talking about. You want to find basically M theta times theta dot plus C theta. Let me write TH, T dot TH dot plus G theta equals tau. Let me just simplify this. TH d dot. So the d dot means it's second derivative. Okay. Okay. So first of all, if you want to find the mass matrix, you just take the Jacobian. Okay, and I'll talk about Jacobian next class. Next, I said once you find M, now the question is, can you find these two terms? Well, what you do is you take these equations of motion, you sub in alpha 1, alpha 2 equals 0, and that means that you're left with this part. So that I've collected as N. Okay, N is C plus G. Now within the C plus G, if I need to extract out C from G, then what I do is I take this N, which has these two terms, I put omega 1, omega 2, which is basically the velocity, theta dot, equal to 0. If I do it, then I will extract out G. And then finally, if I want to find C, I take the N, which is these two terms, and I subtract out G to get C. And that's how I find all these terms, M, C, and G. So once you get this, you copy paste inside the double pendulum code, which now is similar to the projectile code. There is a part which does RHS, which basically takes all the equations and puts them here, including the torque. There's a part which does the ODE45, just like we did for the projectile, where we supply the right-hand side, we supply the initial condition, we start the double pendulum in a position where it's actually arm stretch. So if you take your left arm and if you stretch it horizontally against gravity, then that's the position you start with, and then it just integrates. And then I do some animation, which is this part. And so you see animation once I do this, once I run this. So you can actually change the speed of this. There's a command called FPS. If I change that to 30, I should be able to slow it down. Maybe this looks a little bit better. Okay, so what I did was I also wanted to show you the effect of putting a torque. Now there are two torques. There's one torque at the, so one way of thinking of the double pendulum which I showed you is like, think of the double pendulum like your hand. And so the way I would like to describe it is the first link is basically your the upper half of your arm, and then the second one is your lower part of your arm. And so the torque one is the shoulder torque, and then the second one is going to be the elbow torque. Okay, now what if we put a spring between the upper and lower arm? So we basically replace the torque 2 with a spring. Okay, and the spring is such that when the legs are fully stretched, that is theta 2 is 0, the spring is not compressed, so it's free. Okay, and so let's put 1 first. Okay, there's a weak spring between your upper and lower arm, and then run this. I think there's a problem here. It will not run. Okay, so this is basically the case where the restoring force is positive. It will not work. I need to put a negative value. So this is the spring is sort of pushing towards the equilibrium point versus away. So now it should work. So you can see that the weak spring doesn't do much. There's something happening here, but other than that, nothing's going on. Let's try to make this 10. So now making the spring stronger. And you can see that the deflection is minimal now. It almost looks like a single pendulum. If you now keep increasing the spring constant, let's make it 100 and run this. Okay, now you can see that the spring is so much springiness to it that, or it's very stiff that the pendulum is almost like a single link pendulum. Now here's what we can do is, I started the pendulum in the horizontal position. Let me start the pendulum at 90 degrees. So that would mean I change this to pi divided by 2. And then what I'll do is I'll change the equilibrium point of the spring to be that point, pi divided by 2. Okay, so it's now the free length of the spring is at 90 degrees. And now let me change it to a weak spring on this. So you can see that the weak spring, it just behaves like a normal pendulum. Now let's increase the spring constant. Okay, now last part. Okay, I'm almost done. Was to put a damping term. So I put a damping term here. The damping term is proportional to the relative speed of the two links. In this case, the relative speed is the rate of change of theta 2. So it's omega 2. And so run this. So here the damping is actually quite substantial. If I remove the damping, it will actually swinging crazy, right? So if I make this 0, you saw that it's actually spinning crazy. Yeah, so it's turning, but if you put a damping of 1, well, maybe I should go 0.5 and go slowly towards 1. So here's 0.5. That's actually substantial damping, apparently. That's almost slowing it down. It's not letting it freely turn. Yeah, so you could add damping, you could also add a spring, and then see what the effect is.